All right, let's jump right in. We're going to break down a term you hear all the time, but what does it really mean? I'm talking about software engineering. We're going to look at what it is, where it came from, and why it's, well, basically running our entire world now. So let me ask you something. Think about an MRI machine at a hospital. Then think about the app you use to get a ride home. And then something totally different, like an intercontinental missile. I mean, what on earth could those three things possibly have in common? Yep, software. It's the one thing that connects them all. We're talking millions upon millions of lines of code running silently in the background of, well, pretty much everything. It's the invisible engine powering our money, how we get around, how we talk to each other. But that brings up a pretty scary question. What happens when that invisible engine just fails? And that's where things get really serious. Because when software breaks, it's not like a typo in a document. The consequences can be absolutely devastating. And I'm not talking about hypotheticals here. These are real-world disasters. You've probably heard about the Boeing 737 MAX crashes. That was a software flaw. Or the Ariane 5 rocket that literally blew up just seconds after takeoff because of a single data error. A satellite lost in space because of a missed command. Heck, even when Amazon goes down for just a little while, we're talking millions of dollars lost. The stakes, they just couldn't be higher. You know, there's this great quote from Paul Ehrlich that just hits the nail on the head. To err is human, but to really foul things up, you need a computer. And it's so true, right? A tiny mistake made by one person can get baked into a piece of software and then amplified by a million, turning it into a catastrophe. So you might think these are modern problems, but they're really not. The roots of this go way, way back to a time that almost brought the entire computer industry to its knees. They called it the software crisis. Okay, so picture this. It's the late 1960s. Computers are suddenly getting incredibly powerful, like going from a bicycle to a rocket ship. All of a sudden, we could tackle these huge, complex problems we'd only dreamed of before. But there was a massive catch. Our ability to write the programs, the software for these new superbrains hadn't caught up at all. The complexity was just growing way too fast for us to handle. And the result? It was pure chaos. I mean, projects were always late, they cost way more than anyone planned, and if you were lucky enough to get something delivered, it was probably buggy, slow, and didn't even do what you asked for in the first place. You just can't build the future on that kind of shaky ground. And get this isn't some dusty old history lesson. A study by the Standish Group looked at thousands of modern tech projects and found that a whopping 2/3 of them, 66%, end in either partial or total failure. Why? Well, it's often because they forget the lessons of the past. They don't have clear goals, they don't test properly, they don't manage the complexity. In a lot of ways, that software crisis never really went away. So clearly, something had to change. The answer that emerged from all that chaos was a brand new way of thinking, a new discipline. The idea was to stop just writing code and start building software with the same kind of discipline you'd use to build a bridge or a skyscraper. And that is where we get our official definition of software engineering. The key words to look onto here are systematic, disciplined, and quantifiable. This was a total game changer. It was a move away from the idea of a lone coder hammering out a program towards a formal, predictable engineering process that a whole team could follow. So let's really spell out the difference because this is super important. Think of it like this. Programming is the act of writing the code. You have a problem, you write code, you solve it. But software engineering, that's the whole shebang. It's a team sport. It's about thinking about the entire life of the software, from the very first idea on a napkin to the design, the building, the testing, and all the way to keeping it running for years to come. The goal isn't just to solve one problem. It's to build something huge and reliable that can grow and change over time. Okay, so that's the what and the why. But how does software engineers actually pull this off in the real world? Well, they have a whole toolkit of processes and software designed specifically to keep things on the rails. Let's walk through a pretty standard modern workflow. First up, everything starts with what's called version control. Think of a tool like Git. It's like a time machine for your code, letting a huge team of people work on the same project without stepping on each other's toes. Then, you've got project management tools like Jira. This is the command center, right? It keeps track of every single task, who's doing what, and how close you are to being done. Next, and this is crucial, you have automated testing. This whole process is often called CI/CD. It's like having a robot that, every single time a developer makes a change, runs thousands of tests automatically to make sure nothing broke. It catches bugs instantly. And finally, you have other tools that are constantly scanning the code, looking for security holes or parts that might be hard to fix later. See, every step is a safety net, an engineering principle put into practice. And when you put all of that together, the principles, the teamwork, the tools, it allows us to build things on a scale that the folks back in the 60s couldn't even have dreamed of. I mean, just look at the sheer scale we're talking about today. The software that flies a Boeing 787, that's about 6.5 million lines of code. The browser you might be watching this on, Google Chrome, almost 7 million. And then you have something like the Facebook app, a mind-blowing 62 million lines of code. There is just no way, absolutely no way, you could manage that kind of complexity without the discipline of software engineering. So, at the end of the day, software engineering isn't just a fancy name for programming. It is, without a doubt, one of the most important disciplines of our time. It's the blueprint, the scaffolding, and the foundation for the incredibly complex, interconnected digital world that we all depend on every single day. And so that leaves us with one last big question to think about. As our world gets more and more automated and software gets woven even deeper into our lives, controlling our cars, our medical devices, our finances, what is the ultimate responsibility of the engineer who builds it all? It really boils down to safety, security, and maybe most importantly, trust. And that's something we should all be thinking about.